I am. All right. Ah, okay. It works. Oh, you guys are all online. Probably could be heard. Um, okay. It works. Oh, you guys are all online. Probably could be heard. I was just letting you know that anyone who's watching, just know I can spell it later. It works. Oh, you guys are all online. Probably could be heard. I was just letting you know that. It's a serious lag. Okay. Right. Mm-hmm. Slideshow. Hello. So, my name is Lachelle Foley, and this is Chugalug. Good evening. And this is sort of a tough topic or something that might sound scary to people, but I'm going to try to make it not so scary, or at least make it understandable what we're doing and why we're doing. So I work with a group, and one of the things we're doing is trying to produce source code that is user friendly, essentially, to users who are not necessarily programmers. And that's a little bit of a challenge, but I'll try to explain why we want to do. Yeah, uh, the primary language is C++, but there are others. Yeah. Um, so I am a chemist. I'm a scientist. Currently modeling carbohydrates, mostly in a biological context. I've been using Linux as my primary operating system since about 1994, and I started using Linux for science, and that's the main reason that I've ever used it, and that explains why I know almost nothing about how to use YouTube, and it took me forever to get it set up. So, uh, that's why you got what? Linux is for science. Yeah, yeah, yeah. Me too. Yeah, it was just suddenly I had so much more freedom. The open source software is really great for that. Um, because my interest has always been the science as my focus, I have very little formal computer training. Took a couple of classes, but mostly self-taught from books or from the internet. A Fortran class in undergrad and a C and Unix class in grad school. That's kind of it. You have a question or the same way? Yeah, yeah. That you can learn a lot just by messing with things, just seeing what happens. I do lots of computer work. This will become clear. I do. I'm sort of the that unicorn, the full stack developer or DevOps. I do, like I receive the package and open the box and plug it into the wall and everything all the way up to explaining to the customer how to use the software. But not every bit of all of that. There's a team that works with me, and happily there are things they ask me about and I don't know. I'm always very happy when that happens. So anyway, I work with Rob Woods, mostly at the Complex Carbohydrate Research Center. A little bit about science. Scientists, if you don't necessarily stop and think about it, but the whole point of science is to do something that nobody else has ever done before. And that means you're doing totally new things. That's the whole point. That's what science is. And that means that scientists often have to build equipment and they have to learn multiple skills from all over places. You have to learn electronics and plumbing and carpentry and glass blowing and optics and vacuum pump technology and rocket building or whatever it is that you do. You have to learn a whole lot of stuff from some other skill set so that you can build whatever machinery you need to do your science. And this also applies to computers, of course, hardware, software, and sysadmin. Generally, scientists have to know a little bit of all of that, and that's how I turned into a unicorn. Others usually don't know much about your work, which makes it a little bit of a challenge because not even other scientists really know what you're doing, and that's, as I said, you're doing something brand new, so that makes sense. It's not that you're, so special. It's just that you're wandering off into territory that other people have not gone into. Hmm? That's why you're doing science. Yes, that's the whole point. If someone's already done it, then you say yay and move along. But sharing is good. So we need to, whenever a scientist does learn something new, they want to get that knowledge out. And the trouble now really is that traditional publishing only speaks to other scientists with very similar backgrounds, and they're not necessarily all the scientists you need to talk to. I mean, certainly they have to be there to peer review and make sure that what you're doing makes sense, and you're sort of checking each other's work. But we need the science to be translatable so that other scientists from other fields scientists that specialize in other fields can use your science, right? And we want to reach everyone, and that can be a little bit challenging because everyone includes lots of people with PhDs, and so we don't want to insult their intelligence, but we kind of have to keep things simple because although someone may have a PhD in one subject, they know a lot about that, they might only have a high school or college level knowledge in your subject. So yeah, or okay, so the comment was someone may have a PhD in weather, but they can't blow glass. That's one thing, or even science to science. So, or uh, someone who studies botany could do that without ever really learning the three-dimensional structure of carbohydrates. This is the serious nitty-gritty chemistry. Even though carbohydrates are important to them, they have no reason to know those sorts of details that a chemist would know. And they took intro level chemistry in their first year of college 15 years ago, and maybe they remember some of it, right? So when I say I go on to the next point, I say we're going to assume an early college level for most of the topics that we try to present to the people outside of our specialty. And, I don't mean that as an insult. I mean that as really this is just sort of what you can generally expect for people who are in different specializations to know about everyone else's specialization. And we do have to assume no advanced computer skills because a lot of these people also don't have computer skills. So they don't know our science and they don't know the computers. But what we want to do is get our science that we do on computers into their hands and let them be able to use it. And we would also like them to be able to handle very advanced situations. So they've got some really great idea and they need to do something special, which is what scientists do. Then we want them to be able to do that. So we have some non-traditional ways we share, and that's kind of what this whole talk is non-traditional ways to share. And we have websites. Glycam.org is our production, or we call it Glycam Actual. Actual is the name. That's our website that is the live running one that we try not to break. And we have dev.glycam.org, which you can go to, and at any moment that might be up or down. There's no promises because that's where we're doing, that's our like last development line. We do most of our development further down, way in the background, but we have this one last live site so that we can test everything in an actual live environment and make sure that it's working properly. And then sometimes, of course it's not, and that's why you have a development site. But I'll show you that one because that's the one that's the furthest along right now. And I also want to apologize for all the words in this presentation. I usually do a lot more graphics, but I'm really busy with this project right now at work, and so I couldn't spend a lot of time. So pardon all of the words. I will try to make it interesting nonetheless. We make software. We make applications, as in programs that someone can run in the traditional sense of an application. We make application programming interfaces, things that you might use to make your own application that's different from whatever application we might have programmed. And most especially in the topic of this particular presentation is the source code itself. Source code is good for a variety of reasons. One, it tells other scientists exactly what you did. If the scientists can look in the source code and read it, they know exactly how something happened, and scientists often need to know that. That's why they take notes. So our source code and our scripts, those become sort of our lab notebook. That's where we keep the records of all the things that we do and how we do them. But the source code, if the source code is also usable to the science, and to the other scientists, if you can make it where they could easily understand it, just jump in, figure out what's going on very quickly, and start adding to it, modifying it, then you've got a situation where the scientists can really very rapidly develop new things and move forward. So I think of it like a breadboard. Some of you who know some electronics may have heard of breadboards, and it's just a hole with a little plate, sort of a surface with a bunch of holes in it, and you can stick wires in and such. It's made for prototyping and testing electronic equipment. And I thought years ago, I need the source code version of a breadboard. I need something that I can quickly, rapidly get in there and try out new ideas. It's not necessarily going to be super efficient code. It won't be fast, but it'll be easy to use, and I can make new stuff with it. And that's sort of where all this started, is I needed that for me. And I started writing it, and then other people was useful to them. So anyway, we also do training and talks like this one, and we have a video online, which I hope that we will get to. I'll show you our video. It's a really cool video. Actually, we've got a couple of videos. I don't think they're all up yet, though. Okay, so here's I do have some pictures about the science. So here coming up are some concrete examples of the kind of things that we do and that will become easier for other scientists to do when we have these tools fully developed and deployed and out in the world. The slides I'm going to show you come from various group members, but most of them are from Oliver Grant. He's giving a different view of this similar topic to the biochemists, glycobiologist people, and so his slides will show that. And he happened to have them available at his fingertips and said, here, use these, so I'm using them. The slides would look a little wonky because I didn't try to remake them. I just sort of shrunk them and resized them, and things might be too skinny or too tall or too fat or something. First thing that is important to know is what some of the other things you're going to see mean. So, there it is. Okay, there's my mouse. So this little stick figure over here, all the red things are oxygens and the gray things are carbons, and we're not showing the hydrogens because they just sort of clutter up the picture. This is a picture of what we call a glycan. This is a carbohydrate. It's a bunch of different carbohydrates. And people who do glycobiology are used to glycan means carbohydrate. Glyco is a prefix, or for carbohydrates, so carbohydrate biology, glycobiology, and glycans are carbohydrates. Anyway, they have developed these little symbols to mean the different types of carbohydrates. The purple thing is acylic acid, the yellow is mannose, the blue is an N-acetylated glucose, glucnac, is related to the glucose that is important to diabetes. I'm sorry, yellow is galactose, green is mannose, red is fucose. So this is a 3D representation, and then the two bottom frames are 3D representations of all, these are all the same structure. You'll see a lot of representations that look like this one, this 3D thing here, the cubes and the spheres and the little cones. And we do that to make it very easy, and you'll see why, to understand pictures. Because if you look up here, that just looks like a bunch of the same stuff. You can't tell that these are different things just looking at it, right? But here, now you can tell what the things are. And this is what makes carbohydrates so difficult to model and to understand, because if one of these little oxygens is in the wrong place, it's all wrong. It's all different. And it's really hard for even the experts to just look at that and say, oh, that's, this or the other. And it's really, really sort of challenging in this three-dimensional way. Sometimes we take these three-dimensional images, little green spheres and such, and we put them inside of the rings. So now you can see everything around this green sphere, that's a mannose, there's another mannose, etc. So anyway, these are images that you'll see. And here's an example. It's lovely. It's even a video. Yes, Oliver gave me a video. I didn't realize I had a video. Yay. All right. So this is, I'm pretty sure this is GP120, which is a protein from HIV, human immunodeficiency virus. So this is the thing that sits on the outside of the virus and is part of, the business of the virus, how it makes things happen. So the red parts in this picture, the red parts are protein, and this is sort of a surface of the protein being shown. So you can see what the surface kind of looks like. And the other things that you see, the little spheres and cubes and such, those are the glycans, just like what I showed you on the last slide. And the glycans are really important because viruses and other nasties like bacteria, fungi, etc., they will use glycans as camouflage. So what they'll do is they'll get into your body, and then they'll take glycans that are part of your body, and they'll stick them to their surface so that your body's defenses think that they're you, right? And they won't attack. So this is, hello. Oh, and by the way, interrupt me at any point if you want to ask questions. I don't mind that, really. Not that you have stopped. That's good. I do appreciate it. So anyway, all right. So like I was saying, they take these glycans, these carbohydrates, and they put them on their surfaces so that they look like the host. And your host, actually your body, many of the cells in your body have these same carbohydrates all over it, and that's how they're able to do this. They just look like other things from your body. Here's another example. We have something called the Protein Data Bank, this PDB, that's what it stands for, Protein Data Bank. And it's a big database of three-dimensional structures of all sorts of proteins and things associated with proteins. There always has to be a protein in the PDB structure, but it can have other stuff too. And there are way over 100,000 entries, and some entries contain multiple carbohydrates, some entries contain no carbohydrates. So this 100,000 carbohydrates includes the fact that some entries may have 10 or 15 carbohydrates, some may have none, but there are like 150,000 entries in the PDB right now. We can find out exactly if you're curious. Anyway, the PDB was made for proteins, Protein Data Bank, and many years after it was made and really, moving along rapidly, they figured out, oh, we have to support all these other types of molecules. And so the support for the other types of molecules is not great in the PDB, and we're trying to change that rapidly. That's one of the things my group is working on. And so we have gone into all of their entire database, and we go looking in the structures, in the 3D structures, and just based on coordinates and element type, we have software that goes and figures out where all the carbohydrates are. And so even if a researcher, so researchers 10, 15 years ago, they maybe didn't know how to figure out what carbohydrate they had or whether they had it right. Or sometimes the carbohydrate wasn't the part they were interested in. It was just sort of stuck on a protein somewhere else. And so they didn't pay a whole lot of attention to it, right? So sometimes the structures aren't that great. And I don't want to fault the scientists. This stuff is really, really, really hard. And they were solving other really, really, really hard things. And the carbohydrates were just sort of peripheral. But now we would really like to go back and get all that information about the carbohydrates and have it be right. And so one thing that we're making is this Gly Finder. And the Gly Finder will do that. It will make it very easy for people to search the whole protein data bank and find all the carbohydrates and then go and look at them as they wish. That's something that's impossible to do right now, except that there's this website you could go to, and now you can do it. And we're mostly good. We've got some bugs to work out still. It's not perfect, but it's really, really good so far. Another thing that we do, and this is the important part. Notice that says tailor-made tools. So these 4 people are scientists from outside of our group. They're not our group, and they're working on this sort of thing. And so I really was just sort of peripherally. I was in the room maybe, or in a video conference maybe. But people in our lab made this particular tool. Oliver Grant primarily. Anyway, the tool, let me explain what this does. This thing that you're looking at, this is HA. So when you hear about virus, the flu virus, and they say it's H1N1 or H7 blah, 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 whatever it is, the H is talking about this thing right here. So this is the business end of one of the spikes on the surface of flu virus. This side is in the flu virus. That's what anchors it down to the virus, and this side is sticking out. And this side has 1, 2, and you can't see the third one on the back side, but it has 3 sites where it goes and grabs onto carbohydrates. And you can see little carbohydrates. There's the yellow, there's that little yellow sphere and a little purple diamond, right? So it's got little carbohydrates in there. And these things grab onto carbohydrates, and that's how the flu knows that you're something it wants to infect, is based on your carbohydrates. The carbohydrates on your cells are different from the carbohydrates on a bird's cells, or statistically so anyway. And so the flu virus goes and binds. And so what was kind of interesting is we'd have these glycans, and from earlier you have some idea what these things mean, I think still. And if you look at these, the only difference is that this little repeat unit, this gluconate galactose, or blue square, yellow circle, that repeat gets longer and longer in each one of these cases, right? So what happened is there's no binding here, there's no binding here, suddenly there's high binding, and what's happening is these guys are finally long enough that they can span from here all the way over to here, and these and this are hooked in at the same time. And so when you have 2, it really binds well so you get this extra potent binding. That's all very interesting. The point how this comes in with this talk is we had to go make this tool for them, right? What would be great and is if we could make it so that they could have gone and made this tool, right? Or easily made it, and it's not that we don't want the work. Well, we're kind of busy actually. We can't do everything, so someone else please come do it. But yeah, so what we're trying to do is we're trying to make computational tools that are easy enough that scientists who are not computational specialists and they're not carbohydrate specialists can at least do some really cool stuff without us having to do it all for them, or other scientists that specialize in our field, right? So not that we like them, they're all nice people, but if they could do their own work, and that would just be awesome, because they could get so much more done than we could possibly do. So how do we do this? Because once again, scientists are doing things that have not ever been done before, and that means that software doesn't already exist most of the time. If it did, then you're not doing something new, right? And it's also impossible to write software that guesses what a scientist might need. So as soon as a software company makes software and publishes it, the scientists all jump on it, and they do all sorts of things with whatever was already written into that software package. But very quickly, oh, now we need more stuff, because we've already exhausted all the stuff you got there. So And we can't guess what they're going to need in the future because they're doing new stuff. So it would be great to just give them code and give them code that makes sense to them, is organized for them, uses words that they recognize, is is well enough written so it's easy to see and understand and read. It's not necessarily made for super efficiency. It's not for elegance of algorithm. It's for, can someone relatively new get in here, use it really quickly, and get going. So that's what when I say the code is the product, that's what I mean. We're trying to get them code that they can use to make into whatever they want. So it needs to be easy to use and well organized and well documented, and this is really hard to do, by the way. Anyway, but our strategy, the strategy in general for all of this dissemination, getting things out to people, that we've adopted is first we have something called scenarios. These are question-driven, what happens when a glycan binds to my protein? Question-driven scenarios where we just lead the researcher by hand through, you would do this and use this software and then this and do that and do the other. And this is how you might answer this question. And this is for people who are totally, totally new to the whole concept. And then the scenarios, the scenarios all use web tools that are available on the web. So the idea is once they've been through a scenario or two, they'll understand what the web tools are doing, and then they can go off and make their own scenarios by stitching together the web tools and using them in new ways, right? Once they've used the web tools, and if that's not enough for them, we have a layer of Python layer, and Python is very, very easy to use. You can get up to speed rapidly in Python. Programmers love it because of this. And so we have this Python level that we call GEMS, GlyCam Extensible Modeling Scripts, or System, or the meaning of the acronym changes occasionally according to who says it. But the main star is GMML, GlyCam Molecular Modeling Library, and that's C++. So C++ is low enough level that it can be really fast. You can actually get some efficiency and some speed, and you get incredible flexibility. So a little sort of sidestep. My original version of GMML was in C because that was what I knew. I knew C. And I started writing it, and people told me, oh, you don't want to use C to do that. You want to use Perl or Python. And Python was just becoming known at that time, but Perl was just all the rage. And there were lots of scientific packages for Perl and what have you. But, of course, the problem was I was a scientist doing brand new computational stuff. I couldn't really use that many of the Perl scientific packages, and some, but not that many. Mostly what I needed to do was totally new. And there's a level of complexity of what you're doing that after which Perl is actually harder. C was easier to use once you get to it. Perl is interpreted, so is Python. So yeah, Perl and Python, the advantage to those sorts of languages is you don't have to declare integers. It figures out what your type is. It does lots of hand-holding. You don't have to compile your code and what have you. But all of that making things easy is all, little tiny bits of bubble wrap that after a while, when you're having to peel back the bubble wrap to do the more complicated stuff in the background, it's easier to just go use C in the first place. And it just really, yeah. And I was doing, I'm not a scientist using modeling. I'm a scientist doing, making up how to do modeling. So, this is, it gets a little complicated sometimes. So anyway, GMML, star of the show. Again, GlyCam Web for people with completely different disciplines. Let's see, did I say anything new? Oh, yep, the C library I explained. So anyway, we're on GitHub. I'll show you all that in a few minutes. So this is really hard to do. Making this library is hard because, first, the knowledge burden, the amount of expertise that's required is enormous. To make this, we're trying to make it easy for someone else, but in order to do that, we have to really know what we're doing because we have to know how to arrange it so that they don't have problems. And so people have to know both the science and the programming, and often some sysadmin and website design and graphic illustrations. We have to learn a lot. But the students who come in are mostly who we get to work with, which is great. I like students. Okay, yeah. Just everybody, the lag was, I was just making sure someone else was okay. So most of the coders are students, and this is good because they have knowledge similar to our target audience. So I can always learn immediately, what are the things that the people we're making this code for aren't going to know. It's also bad because it takes them a while to figure out what's going on. And yeah, and then the students come in. They've either got some computer background or some chemistry background. Usually, they don't have both. So I'm always teaching coding to the science students and science to the coders. It takes a lot of time, and everything else is really new. File systems, Git, what does architecture mean? Science. Everything that has to happen is really new to all of them, and it's it's hard. And okay, I'm mostly self-taught, which meant that when I first started on this project, this is an enormous project, and I've got, different people helping, to write it. I don't even know how to tell them what they need to do, right? Because I've always written code, it was all in my head. It was my own baby. I knew everything and everything where everything was, and now I got to somehow, delegate that. It took me a while to figure out how it is. It's a big shift, and it took me a while. And there's no way that I could do all of this all completely by myself. I'd never have time unless I just didn't do anything else. So yeah, it was hard. So I finally learned some tools and some things to say that could really help. But yeah, it was really hard. One of the things, this architecture word, it's pretty critical. So this is sort of the target architecture for GMML, and so we have input that comes from lots of different places. And so it can be input from users or input from data sources, right? And the input comes into analyzers and or manipulators. So we analyze the PDB structure and see if there are carbohydrates, or we manipulate the PDB structure, or we manipulate something else to change a bond angle, or move something, or change the name of an atom that has been misnamed or mislabeled or something, right? So we have manipulators. The main part here is here, really, the molecular data structure and the molecular metadata, and then you have output writers. So this is where everything really stays. Everything comes in here and you do all your work here. And what that means is you don't care where anything came from and you don't care where it's going to. You only have to write the guts of the program once, right? So that's sort of the architecture. Getting people to be in a hurry and under deadline pressure and still stay on architecture. I mean, I even have trouble doing that. I can't hold it against all the rest of them who do, right? So, it's hard. But let's go see the websites now. So this is dev.glycam, and so to give you, I'm going to show. Okay, this is the development site, and I'm doing this live, and something might break. Anyway, this is what we call a carbohydrate builder, and you can see that I'll have to show Dan how horribly that worked. I'm using a really low resolution screen here to make this ancient projector happy. This looks a lot better on a real screen. This off to the side. So this is an illustration explaining how to build your carbohydrate. Anyway, okay. So now I've got a little galactose. You see there's also a little word, GAL, MAN, XYL. So that's for the people who don't know the symbols. They can use the letters to tell what they're building. And when I get done, will this work? Woo! All right. Yes, it worked. And I can go and visualize a 3D structure, and this is a mannose, right? So this is and of course they can build more complicated structures. I'm not going to try to do that here, right? But yeah, very, very nice. So that's carbohydrate builder, Glyfinder. So I'm going to build this. This is an old version of our site, of our builder. And we're actually trying to figure out which one we really like and where. But anyway, here it's found all of the mannoses in the PDB, and there's I guess 6,915 of them. And if you want to see it, aha, and will it work? Ah, It does. All right. So here is that. Look, there's a glycan, a couple of glycans, even a couple of here, little blue squares, right? But anyway, you can very, very quickly, it retrieves the information from the PDB, and then you can view your the molecule. The little ribbons, these ribbony bits, those are the protein. So that's in the same way that these little 3D structures represent specific types of carbohydrates, these ribbon sort of shapes tell you a lot about how the protein is structured. They give different information because different information is important to most people, but these are just representations. You would see balls and sticks, but you wouldn't be able to see any real information. If I if we saw all balls and sticks, it would be kind of hard. So anyway, lots of mannoses, and we have some other things available, but I'm not going to go there. This is our our production site, and it still works pretty well, but it needs to be updated. And so, this is our updated site, which will be much faster and easier to maintain and update and what have you. So I've had to learn about Django and Docker and Apache and Python, all many things. Let's see. Here's our GitHub. We have a development team, GMML and gems. So here's the actual source code for GMML. It's all in it's in C++, and there are, I don't know how many lines of code. This is enormous, really. The dev branch is the most up-to-date one, and that's this. I was at one point looking up the amount of code. Yeah, okay, so I looked at the amount of code that it takes to make that happen. If you count everything, and this is stuff, almost all of it is stuff that we've written. A little bit of it is we borrowed some software from somewhere else, but probably also the counting software didn't count some things that we have that are code that just it didn't see. So counting absolutely everything from how do I build a development environment so people can develop way in the back end, know what the website's going to look like before it goes live, and then develop there before it goes, it goes live on the development site, and then it can go live on the production site, right? How to make all that infrastructure work. There's code that had to be coded from scratch for the most part because we need we have to run simulations in the background. We need really complicated stuff. If you count that and all of the development code and the website code and gems and GMML, all of that was about 1.5 million lines of code, which is an enormous amount of code. And it's, yeah, anyway, I didn't get around to figuring out exactly how many lines. I think that GMML by itself is probably in the 70,000 range, but I don't know. And let's see. So we have pages explaining how to use gems and GMML. So we have gems is the Python level. By the way, what gems does, or how this works, how gems works is, let me go back up here. Nope. Here. Let's see. Okay, GMML is in C++. There's software called Swig, S-W-I-G, as in take a swig of beer. Software called Swig that you can tell it, my low layer is C++ or Fortran or C. It has a nice long list, not everything, but a decent list of low level and upper level scripting language, Python, Perl, Ruby, PHP, etc., the scripting languages, and it will create you a translation layer between those two so that you can have the speed of the C++ below, but you're using the scripting language to orchestrate all of the functions in your source code at the bottom. So that's, it turns out to be a really good way to do it, and sorry, I don't know, I'm having trouble remembering which direction my screens are. Question, yes, let's see. So, yeah, really simply, GMML has a big central data structure. Some information comes in, you do some stuff with it, and then you put it out in some other form. And that's mostly what it does. at that level, it seems incredibly simple. You read in stuff, you do stuff to it, and you write it out. That's kind of what all software does. Um, let's see. Uh, Doxygen documentation. We have there's a class list. So, oh, why am I not? This is probably not up to date. Not with that. Ha! Wow. Uh, where's Adam? All right, so I'm having a heck of a time making this work the way I want. Molecular modeling. So this is not as well organized as I would really like it to be. We're working on that a lot too. Anyway, um, the assembly is our main structure, and it contains atoms and residues. And you see there's lots of code written for using the assembly. Here's atom structure. The atom structure has some parents. This is something multiple inheritance is called. And for a lot of people, it doesn't work well, but for our situation, it's perfect. So we can have an atom, and things always happen on atoms. But sometimes the atom has sort of multiple parentage. So an atom can sometimes be looked at as a quantum mechanics atom, or as a molecular dynamics atom, or as an atom from a crystallographic file, or something like that. And so these multiple parentages for our atoms, we use multiple inheritance for that reason. And it's better because your code sort of focuses here, and it just sort of goes up and gets other information as it needs it. Anyway, making all of those decisions, every little bit like that is just really hard. Let's see, yeah, this is this again. We have a listserv where people can write and ask questions. Anyway, yep, that's basically what we're doing. I'm happy to show code to you or show how things work, talk a little bit more, but that's basically what I want to say. We're trying to make software that does something, does it right, but the source code itself is easy to use and readable. Yeah. Okay, the question is, what is the process that we use to decide what we're going to work on and what we're not going to work on? As in, okay, so uh, the putting it together, by that you mean how do we organize the software, and or do you mean no? Okay, you don't. You're just, open-ended question. All right. How we decide what we're going to work on? Probably the first and foremost thing is what we've got funding for, right? If a funding agency has given us money to do something, and this is mostly funded by the National Institutes of Health, by the way, which probably isn't surprising. And money, they've given us money to do something, then we got to do what they give us money to do, right? And now within that there are always options of exactly how you're going to go about doing it, right? So a little bit the development of this is driven by this is what we needed to do for the grant money we got. The market forces, yes. But at the same time, we try to, even when we're adding code to the GMML to do these little projects that we have to do, we try to stop and think, okay, how is this going to impact future code that gets written? And is it going to make it easier to write future code or harder to write future code? And we try to come down on the side of something that makes it easier to write future code. So, but there's always there's, and anyone who's done any housework or anything else, really, there's always a short, easy way to hack something together that'll last for a little while, just long enough to get through, and then there's doing it right, right? That usually takes a lot longer and what have you. And there's, the old thing, if you don't have the time to do it right now, will you have time to do it again later? And a lot of times we ask that question, and it's like, okay, if we think there's a good chance that we'll have time to do it again later, and we don't really have time to do it right now, then we will hack something together. And that's one of the hard things is the decisions you have to make. You can't have it all be right. Um, we talk. We have a meeting every week, and we really discuss how things are going to be arranged, and I'm sort of queen of the meeting or whatever, but I really try to make sure that everyone that there's consensus, right? So the programmers, this is one of the things that makes it hard too, is that they're doing creative work. They're making stuff up new from scratch. And if their hearts aren't into it, they're not going to do it. Even if they're trying to, something in their head's going to make them get stuck and they're not going to do as good a job. So whenever we make a decision, I really want to know that they're all with me. They really want to, they think it's the right thing to do, or at least it's an okay thing to do, and so, huh? They have to buy into it, yeah. And if they don't buy into it, I know I'm not going to get as much work out of them as I need. So I want them to really, really dig it. I also want them to know how important this stuff is because people use this to make drugs. One day you might be injected with a drug that someone made, with inspiration from this code that you wrote. So think carefully, do it right. Um, and that's true, and no pressure, right? But yeah, it's hard to decide, and then there's always a competing of there's never enough time and there's always too much work, right? And you always have to sort of choose what to do. Um, One of the things that's been kind of good is the there's sort of a critical mass of people who've had enough experience that they understand um, they that we can make pretty good decisions about where we really need to do it right and where we really don't have to do it right, at least not right now. And something else that we'll try to do, if something is hacked in, we try to separate that out, make it a totally separate piece of code, a totally separate function, not something intertwined in the middle of your big important code. Make that separate so that later doing it right. Right, right. So later changing it is just I take this code out here and I put new code in there, and the rest of the function had, or the process method, whatever, had no idea what was going on in the background. And that's a fundamental programming thing, but sometimes it's hard to remember that. Hard coding, we really try to avoid. We can't avoid hard coding. I'm sorry. That's impossible to avoid hard coding. You have to at some point somewhere code in that a carbon atom has 6 protons, etc. Right? There's just like this has just got to happen. So there's got to be hard coding. But another thing but what we've done is it doesn't really show in the code that's online. Made a molecular metadata class where we can take all our hard coding and we put it in one place. And it's away from the rest of the logic in the code, and that makes that ha- one thing, it makes it easier to write all the rest of the code because all you have to you just go look up the information you need out of the metadata. But two, it keeps it makes it easier later to go and change stuff. The dry principle, don't repeat yourself. Yes, the code has gotten very wet sometimes, and the thing that I'm sort of at the tail end of working on fixing was some very, very wet code, soggy, muddy sort of code. And yeah, that was, written by very, very good coders who were just under, enormous time pressure and just had to do something quickly. And so I'm not going to, I don't fault them. They got something done. But, you know, we, we've been sort of, okay, how can we arrange things and sort of put not just fix this code, but put mechanisms in place so that it's less likely to happen again. Give give structure, right? So yeah, there's a lot of discussing about how to do things. We always try to think, how can I write this so that I don't have to write it again? I don't have to change, I don't have to make little variations on it. How can I make it general enough? Think about that a whole lot. And we have happily, we have some computer science students, and they bring in some information to us. But this is one of the things that's sort of interesting about the computer science students, and they are absolutely wonderful. But computer science departments are like it. Think of mechanical engineering versus working in an auto shop. You could do mechanical engineering without hardly, working in an auto shop is not necessarily a prerequisite to doing mechanical engineering. It doesn't hurt. It's going to help. You'll certainly know your mechanical engineering a lot better. But just because you've done some mechanical engineering, that doesn't know that you know what a dipstick is, how to change your spark plugs, whether you have spark plugs, right? Um, is this fuel injected? Anyway, yeah, the 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 computer science students, they are sort of groomed toward that, higher level theoretical. And sometimes we have some that were just, hacks in their spare time and they know some. And that's useful. That's really useful. But even so, they were mostly hacking around for gaming and stuff, and they don't necessarily know the parts that we really need them to know, right? We have so actually, I try to give them computer science. I try to give them learning. Please go learn about this thing and then explain it to me, because that's how I learn stuff. Um, and the science students don't know the programming. It's hard. It's really, really hard. Anyway, yeah. Hmm? Actually, yeah, they are. We have you know, one of the things about programmers, and I'm one of them too, is we're used to working alone and dealing with our own mistakes and fixing things by ourselves. And the lone hero is definitely a personality type, right? The oh, just let me go fix it, and that's great until that person has to leave, and it could happen for so many reasons. Got married, so had to leave for the marriage. Abducted by aliens. Decided we don't pay them enough money to go somewhere. Whatever reason it is, or they graduate and then they leave. Yeah, so we try to pull them in. Yeah, that happens, but usually even they are team players. Like they're in this habit, this is how they do things, but they still care and talk to us. And if we have a problem, they're right on it, trying to help and trying to do things right. So yeah, actually, they're all really the team I've got are really really excellent. So yeah, let's see, anything else? What else? Oh yeah, the we do have a couple of full-time people finally, other than me. That has helped a lot. So another thing with the students is they work like 20 hours a week at best usually, and that's distraction from the main thing they need to keep their head on all the time, which is their studies, right? And so it takes them 6 months before they're really useful, and then and then they're gone in just a short time. That's another reason for designing this really well. Is like when we have this right, a new student will come in and they'll be able to jump into this code and start doing stuff really fast. And the organization of it will discourage them from making it messy. That's sort of the goal. Um, so one of the things that I usually do is I try to give them a project that this is somewhat personality dependent, but usually a project that is in line with something that I know they already know, where they have to learn something new to move them closer to what we need to do, and will also make them learn the code. So, for instance, one of the computer science students who came in recently, the first project he got was really low level sort of memory management. Go fix how these pointers are working and make them work a different way, essentially, or make them work multiple ways. And anyhow, that made him touch all the parts of the code, so he had a really good idea of where everything. By the time he was done, figuring out how these pointers work together and how to do things, he had a pretty good idea of the basic structure of the code. But I wouldn't have given that to, say, a chemistry student, because that would have been, unless it was. Yeah, 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 yeah. So they would get something more like, um, go look at this code and figure out, why something isn't identifying this carbohydrate correctly, or go figure out, something like that, or add, some little function that has to do with science. And, So that's one of the things. There's also often just a whole lot of just teaching them, just sit down with a subgroup of them and just, okay, these are atoms and molecules and they're connected together like this and that. You'd be surprised how much stuff is in here that just people. This is not a complaint. This is not something wrong, but you can't know everything. There are things people just don't know. Like we have to know geometry really well to do this, but lots of people haven't had a geometry class since high school. Maybe they had a little geometry in their freshman year of college, unless that's their major. They just don't know that much, and it was years ago when they last thought about it. But now suddenly, oh, what's a cross product again? Why do I, and so, suddenly they're having to learn all this geometry again or anew, depending on the situation. Um, let's see. Yeah, so I sometimes spend a fair amount of time teaching little bits and pieces of the other disciplines, that they really need to do. So I spend a lot of time teaching. So, new things to make it fit in with everything. What are the guidelines for new things fitting in with everything else? That's what that architecture is about, actually. So, la 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 la. Oh, there we go. Yeah. So the architecture, what that does is it tells you where to put the new stuff. So if the new stuff is, I need to know the angle between three atoms, well, that goes in analyzers because finding the angle between three atoms is an analysis, right? You go and say, so that's an analyzer, it's going to analyze something. I want to change the angle between three atoms, well, that's manipulator, right? I need to know the atomic weight of chlorine. Well, that's molecular metadata. I need to know whether mannose is an aldose or a ketose. That's molecular metadata. I I need to understand a file structure. I need to add a new file structure, some new input file type. Then, that's in data files and input from data sources, right? So that's the point of this architecture, and it is critical, and it's critical for exactly that reason. It's not only where do you put new stuff, but also there's a bunch of code there. If you've ever tried to Google something and you didn't use the right word and you couldn't find it because you just didn't know what word to put in, imagine that with this code. And that's what it's like. If you at least have things organized into little compartments, then I need to look for something that has to do with angles. I'm going to go into the analyzers or manipulators boxes and see if I can find something there, right? So it's really that's one of the things that is really critical for exactly that reason. Just finding things, figuring out where they go. Yeah, yeah, yeah. Or worse, a hotel room where do you know where you keep the rooms? The rooms. Oh, do we call those rooms? I'm not sure we call them rooms. They might be they might have another name. I think they might be chambre. you know, which is a terrible French. Or this is the chamber. This is the parlor. They don't even have a word like room anywhere in the code, right? So, yeah, it's hard. Oh, and then there's the okay. So speaking of building analogies, in architecture, you can get great analogies for a building. Imagine that every time you add a new piece of electronic equipment to your house, you can't just plug it into a wall. You have to run a wire outside to the pole, right? That's just insane, right? But I've seen plenty of code that was essentially like that, right? Every time they did something, they went all the way back down to disk and pulled it up again. It's um, and again, that's usually someone who's under serious time constraint and they don't have time to stop and think and organize, or at least they don't think that they do. That's one thing I've learned is that no, don't take it too far, but in general, the more time you spend thinking about something and organizing, the less time you spend coding it, because you have to do a lot less coding, right? So, for example, oh, wait, what if I just bring one really big line from the line at the street to the house, and then I make this box with like switches in it, and I distribute the power to the rest of the house, right? Um, and another analogy is you think of a house, you go in the house, and there's a couple of rooms, maybe with a bathroom between them. Then there's a master bathroom, and on the other end of the house, there's a kitchen, and maybe there's a laundry room in the garage, right? So now your plumbing is spread all over the house. And that's fine. That's the way most people are used to it. But you could also do it where the laundry and the kitchen and the bathrooms are all sort of clustered together, so that your plumbing's all together. And yeah, and there are analogies in the code to all of these things. How you decide you're going to organize things is really pretty important. It just is, especially when you've got something this big. There's just no other way to do it, make it work. You did? Okay. It's yeah, it's kind of big. Pre-push tests. But speaking of Git, okay, first thing that we've learned recently is make the coders learn Git before you let them touch the code. Just and we're as soon as we're done with this big project, we're going to be looking at how do we make Git tests to make sure that the coders know their Git before we let them touch code. Um, Something you may not realize if you haven't used Git a lot is the first thing a newbie does is if they get something called a merge conflict, they pull a brand new repository, they take their files and they copy it over to the fresh pull, commit it, and push it back. And that's really bad because what you've done is you've just deleted all the code that someone else wrote. All that code that was causing a merge conflict, that's code someone else wrote, and you just happened to write code at the same place as them, and Git couldn't figure out which one to keep, and it was asking you. And, this is knowledge of Git that, people, I have done that, and I realized very quickly what I was doing. Oh my God, I felt horrible, but it's, yeah, yes, yes. Yeah, so knowing Git is incredibly important. Making sure that they really understand Git and yeah, we call it a Git clobber. It's a Git clobber if someone does that. Yeah. Um, the other thing, pre-push tests. So Git has down in the hooks, you can force Git to run tests at certain times, and we've implemented pre-push tests. So you can pull from your buddies and you can commit all you want to, do whatever you want to, make new branches, but if you're going to push back up to the site, you have to pass a few tests, not even long tests, but there are a few tests and you have to pass it before you can push. And that has made a huge difference in terms of the code suddenly not breaking just randomly, right? Because the coder has to know before they push their code back up that they didn't break someone else's code doing what they did. Well, they're in the you can go they're in there. So yeah, so let's see. Nope, not this way. All right, so let's see, Glycam Web, it's GMML Dev. Actually, okay, so the tests are here. At the gems level, the first time someone compiles, the way we have it set to compile is you put GMML as a subdirectory in gems, and gems does make, and it makes everything. It compiles everything. GMML makes the interface, compiles all of it together all at once. Part of that process, what we did was we made it take the tests here and we move those or copy those into the .git it's not into the .hooks directory and into the pre-push. So this tells Git to do that. So if someone has never run, if they've never compiled the code and they still push back up, then they're going to get around this test. And if someone knows what they're doing and they just move this out of hooks, they can get around the test too. But for the most part, people don't want to do that. Or if they do that, they have some good reason for doing this. So and everyone knows that this happens. All the coders understand, what the stakes are. But anyway, so the tests are, let's see, and they are, here are the actual tests. So we have a PDB preprocessor. So the PDB files, we have something that just processes a PDB file, a build by sequence. So we have the way that we specify these glycans, the several green spheres and blue cubes. We have something called a sequence. Let me see. Yeah, here's the sequence that is used in this test, by the way, is that. And D, they come in mirror images. D and L are the two mirror images. MAN, a manopyranos with some things stuck to it, connected to another manopyranos with stuff. Anyway, so this is a sequence. So we have a sequence, and it has to build, first build that central data structure, and then write out another file from this sequence, and that whole process has to work correctly, right? And then we have create an assembly and then write a PDB. We have, I don't, I'm not sure what that means. I'm not sure what that does, right? Huh? Oh, okay, yeah. So, yeah, that's, those are, they're just little tests, that we know. Essentially, whenever a coder has written some new functionality, they usually have to write a program for them to test it and make sure it works, right? So they just make a smaller version of that and stick it in here, something that'll run very quickly, and that becomes the test. So, let's see. Any... We have about 8 minutes left. So, any other questions? Thank you all for all the good questions. That's awesome. Okay. Uh-huh. Oh, the CHUGALUG Git repository. Oh, yeah, there is. Oh, okay. The way I always find it is I go to GitHub, to my site, GitHub Lachelle, and then from there I can get to the CHUGALUG organization. So actually it's github.com/chugalug. So I think if you just go to github.com/chugalug, you may have to put it in all caps like that. I'm not sure. I don't know if it matters. Okay. Yeah. So anyway, yeah, there's there's a website code, and if if someone sends me a pull request and it's reasonable, I'll generally take it. So people occasionally fix little broken links and stuff. And I'm like, oh, thank you. So yeah. Yep. Yeah, the university, I have they only they won't let everyone have access to their servers, so that's one of the reasons it's nice to have this out here is, I still have the security, sort of, I'm the gatekeeper, right, but other people can help by improving the website. That's awesome. Other stuff? And by the way, all of the people who have been working on all of this, they're really, really wonderful people. Any complaints? Yeah, I'm not trying to. Yeah, no, it's not. These are just problems we've encountered and lessons we've learned, and not fault. It's just the way the world is. If everything were already perfect, we wouldn't have a job to do. So, right. Yep. So, anything else? Yeah, so any potential employers listening, go employ these people. They're great. Right. Yeah. All right, well, then I'll go ahead and close this. Oh, I think I know how to stop streaming. Yes. Oh, yes. Here we go. Anyway, hang on. Were there any questions? I didn't even look to see if I got any. Nope, I didn't get any chats. I didn't get any questions, so that's good. I'm not ignoring anyone. Okay, so anyway, take it easy.